Hi everyone, I'm Jiaxin and I'm a second-year graduate student at Wisconsin-Madison. Today I'm happy here to introduce our system called PANIC, which is a high-performance programmable NIC for multi-tenant networks. Nowadays, in 100G network, doing network-related processing takes up plenty of the whole CPU cycle. SmartNIC can help to overcome this problem. SmartNIC is a new programmable hardware accelerator that allows the host to offload network-related tasks into hardware NIC. So in today's multi-tenant environment, one machine can be shared among multiple tenants. Thus, a single server may want to have multiple offloads running on the NIC at the same time. So for example, in the Smart NIC, we may have infrastructure services like network functions and firewall running on the accelerator. And we also have Memcached application and Spark running on the embedded cores. However, the problem is none of current Smart NICs are good at running multiple tenants offload at the same time, and they cannot satisfy the multi-tenant requirements. So what are the requirements for Smart NIC in the multi-tenant cloud? The first requirement is generality. Since different tenants on the host may require different types of offload, the NIC should not restrict the types of offload. The NIC should both support using CPU core or hardware accelerator as the underlying engine, because different types of offload may have different preference of the engine type. For example, implanting the decryption engine hardware can have much better performance than CPU core. And in contrast, CPU should also be supported because many users prefer the programmability and flexibility of the CPU core. Generality also means NIC should support both below line rate offload or variable performance offload. For example, an embedded CPU core on the NIC usually have below line rate performance and unpredictable latency. The second requirement is flexible chaining. Some tenants may have multiple offload running on the NIC. Those NIC should allow each tenant to specify their own chain of offload. For example, when tenant 1 offloads secure remote memory access onto the NIC, the offload chain should be composed by crypto, congestion control, and RDMA offload engine. Besides, it is also important for NIC to support sending packets through offloads in any order, since not every packet needs every offload. Like imagine tenant 2 is running KVS that serves requests from both data center client and one distributed client. The NIC should first decide whether this incoming packet is protected by IPsec. If not, the NIC should allow this packet directly bypass the IPsec engine. So the third requirement we mentioned here is isolation. So when multiple tenants are competing for the on-NIC hardware resources, Smart NIC should provide a mechanism to isolate traffic from competing tenants. And the cloud provider should be able to choose the isolation policy according to the business perspective. For example, we have tenants A and B sharing one unzip engine in the NIC. So Smart NIC should allow the cloud provider to define the isolation policy towards this contented offload. And in this example, we can see the isolation policy is weighted file queuing to allocate the bandwidth of this unzip engine to tenant A and B in the ratio of 2:1. So the last requirement is performance. It is important for Smart NIC to be able to provide high throughput for line rate offload, and Smart NIC should also not incur any additional latency for the low latency offload. Thus, our goal is to build a programmable Smart NIC that meets all these requirements. So here's the outline of my today's talk. First, I have talked about the motivation. Then I will explain what is the limitation for existing NIC, and I will go into PANIC design and show the evaluation result. So looking at the Smart NICs that are available today, we can break down Smart NIC into two main classes, and the first one is Pipeline NIC, second one is Manycore NIC, and we found out neither of them can satisfy our requirements. For the Pipeline NIC, so offloads are arranged in a linear sequence and packet flows through this offload in the pipeline style. Many existing NIC with onboard FPGA use this kind of design. However, pipeline design use static linear topology, thus we cannot send packets through offload in any order, which makes them cannot satisfy chaining requirement. Besides, most of the pipeline design assume the offload can run at line rate. So if any offload cannot run at line rate, it will cause head-of-line blocking, and this will cause isolation and performance issue. In Manycore NIC, network traffic are partitioned across parallel embedded cores. However, current Manycore NIC does not explicitly support isolation, and since there are many hardware resources in the Manycore NIC, like CPU cores, cache, and memory, so to provide isolation over all these hardware resources is not a simple task. Besides, Manycore NIC also suffers from performance issue. This is because the CPU core are involved when the NIC is doing packet routing and scheduling, and it will add significant packet processing latency. So our solution is Panic. So Panic is a new architecture for programmable NICs that support full line rate offload chaining and multi-tenant traffic isolation. Let me give a brief introduction of four main components in Panic that help us to achieve these four requirements. First, Panic uses a reconfigurable match action pipeline to look up the offload chain and isolation policy for every incoming network packets. Then Panic uses the central scheduler to enforce isolation policy and schedule packets between different compute units. The central scheduler helps us to achieve the isolation requirements. To support generality requirements, Panic utilizes a compute unit to attach offloads. The compute unit can either be a hardware accelerator or a CPU core, and it can have either line rate performance or non-line rate performance. Panic uses an on-chip switching fabric to provide high-speed communication between all these Panic modules. The switching fabric together with the RMT pipeline enables dynamic chaining in Panic. Finally, we provision every component's throughput and to make sure Panic can meet the performance requirement for 100G network. In the next few slides, I will first introduce a packet lifecycle in Panic, and then I will go into the design detail in the order of RMT pipeline, scheduler, and compute unit, and finally I will introduce the switching fabric. To help you understand how Panic operates when packets are received, let me use a simple example. In this example, there are three compute units attached to the switching fabric, and Unit 1 and 3 are running service A, Unit 2 are running service B, and when a packet is received in Panic, it is first processed by the RMT pipeline. So the RMT pipeline parses the packet header and look up the flow table to identify the offload chain. So in this example, we can see the offload chain is from A to B, and Panic will then generate a Panic descriptor, contains this chaining information, and attach the descriptor before the network packets. The packet is then sent to the scheduler and being buffered in the central packet buffer. Also, the descriptor is being put into the PIFO queue, which is a hardware scheduler queue. Since there are two parallel compute units, both running service A, the scheduler will use the notion of credit to make the load balancing decision. In this example, we assume compute unit 3 is already busy, thus the scheduler will send this packet to the idle unit 1. After unit 1 finishes processing, this packet is being pushed to compute unit 2, which runs in service B. And finally, the packet is being pushed to the DMA engine and sent to the host. Then let me introduce every component in Panic. Let me first introduce the RMT pipeline. So the RMT pipeline is used to provide programmable chaining and to look up the scheduling metadata. Cloud provider can program a match action table to define their own chaining policy and isolation policy. So here is an example of the table. So when the income network packet belongs to tenant 1, the RMT will look the first row in this table and determines that the packet needs to be processed first by service A and then by service B, and the isolation is weighted fair queuing. The weight for tenant 1 is 3, and in the action state, the RMT will generate a Panic descriptor according to the action table, and the descriptor contains all the information that is required by the Panic scheduler. Then I'm going to introduce Panic scheduler. So there are four main goals for us when we design the scheduler. The first goal is to achieve high performance chaining. Second goal is to load balancing packets between parallel compute units. The third one is performance isolation, and the last one is buffer isolation. So the first two goals is high performance chaining and load balancing. So there are two candidate scheduling methods. The first one is pool-based scheduling, which allow every compute unit to pull the income packet from the queue in the central scheduler. The pool-based method can help to efficiently distribute load to multiple parallel units. However, it requires the packet go back to the scheduler at every hop in the chain, thus it will incur significant latency overhead for chaining. Another approach is push-based scheduling. So in push-based scheduling, packages push from scheduler to engine and from engine to engine. So this approach achieves high-performance chaining, since there is no need to go back to the scheduler at every hop. However, it's hard to achieve load balancing when compute units has variable performance. Like in this example, Unit 1 does not know the load in Unit 2 and 3, so it's hard for Unit 1 to make the load balancing decision. And furthermore, if Unit 1 pushed to Unit 2, but the local buffer in Unit 2 is already full, then the packet will be dropped, and packet dropping will hurt the performance. So our solution is to use hybrid push-pull scheduling to achieve high-performance chaining and load balancing. What is hybrid push-pull scheduling? So in hybrid push-pull scheduling, a compute unit can either pull packets from the scheduler or accept push packets from other units, and the scheduler will switch between push and pull scheduling for every packet according to each compute unit's load. For example, during a period of time when every service in the chain has low load, scheduler will make the packet being pushed from unit to unit in a chain. So this helps to achieve high-performance chaining. If some service in the chain is during high load, for example, in this example, compute unit 2 is during high load period, so the scheduler will change the source route in the descriptor and have the packet sent back to the scheduler instead of the congest service. And the packet will wait to be pulled by another compute unit corresponding to the congest service. This helps to achieve load balancing. In the corner cases, it is possible that even the compute unit 2 in the below figure is during the low load period, but when compute unit 1 pushed, unit 2 unluckily has no space to accept these packets due to a burst. So Panic allows using detour routing to redirect this packet back to the scheduler and avoid packet dropping. The third goal we want to achieve for the scheduler is performance isolation. So Panic utilized a recent scheduling hardware block called PIFO for priority scheduling and multi-tenant isolation. So let me give a quick example to show how Panic provides isolation. In this example, service A is shared by tenant 1 and 2, and the isolation policy is strict priority, which means every packet from the tenant 1 has higher priority than tenant 2. So when tenant 1's traffic comes into the scheduler will calculate the packet rank according to the traffic priority number in the descriptor. So in this example, tenant 1 has higher packet rank than tenant 2. Thus, when the packet is in queue into the PIFO, it will be put in the front of this queue, and this makes the tenant 1's packet can be first scheduled. Previous work has shown that PIFO block can support a variety of isolation and scheduling policy. So for example, a weighted fair queuing is possible if virtual time is used as a packet rank instead of a static priority number. So the last goal we want to achieve is buffer isolation. So PIFO scheduling cannot offer any control over the buffer allocation. With a traditional packet dropping policy, the NIC will always drop the newest income packet when the buffer is full. So it is possible that some high-volume, low-priority flow take over most of the on-chip buffer space, and when a high-priority packet comes in, the NIC will drop this high-priority packet. And with this naive packet dropping method, we cannot ensure buffer isolation. Our solution is to extend PIFO's interface to allow it to support prioritized packet dropping. So as shown in the right, when the packet buffer is almost full and the high priority packet comes in, instead of directly dropping the high priority packet, Panic will first enqueue the packet descriptor into the PIFO array, and then drop the last element in the PIFO queue, along with the packet data. With prioritized dropping, Panic will ensure high-priority packets can always enter the buffer and receive service. and the packet buffer space is allocated to different tenants follows the isolation policy. To support generality, the compute unit in Panic can either be a CPU core or hardware accelerator, and it can have non-line rate or variable performance. The traffic manager inside the compute unit is responsible to send or receive packets from the switching fabric and communicate with the scheduler using credit. Thus, a hardware offload engine inside the compute unit can be designed without any understanding of other Panic component. Finally, Panic uses switching fabric to provide offload chaining for an arbitrary chain. So because it's necessary to forward packets between units at line rate, it is important to build a high-performance switching fabric that every switching port can send or receive packets at full line rate. For example, a crossbar with a bit width of 512 and 250 MHz frequency can achieve our requirement. So it is possible that the crossbar may face some scalability issue when the number of offloads increases. In such situation, Panic can switch to other more scalable topologies such as flattened butterfly to solve this problem. So we implement an FPGA prototype of Panic in around 6,000 lines of Verilog code, including all the components that I have mentioned. So we have also implemented 3 offload engines in Panic, including 2 hardware engines and 1 RISC-V core engine. Our artifact is now public. Please try it out through the QR code. So in the evaluation section, we are trying to answer 3 questions. First, can Panic achieve high throughput and low latency under different chaining models? Second is, can Panic isolate traffic? The last one is, what is the hardware consumption? So first, we micro-benchmarked Panic throughput and latency using pipeline chaining model. So in this chain, every package is sent through 3 line rate units in a sequence. And we measure Panic throughput as a function of packet size, as shown in the right. The result shows that Panic can achieve full line rate when packet size is bigger than 512. Also, Panic can achieve 40 gigabits per second throughput, even with the smallest packet size. We also measure the latency of different packet size. So the result shows that package can be scheduled through 3 units within 0.5 microsecond. So this low latency arises due to the push scheduling. So the experiment proves that Panic can achieve 100G throughput and low latency chaining. So in this end-to-end experiment, we connect 2 SHA units and 2 AES units with Panic, and we generate 3 types of traffic. Traffic group 1 and group 2 are sharing the AES service, and they are background traffic that does not need to be processed by any service. We use weighted fair queuing policy for the AES contention offload. The right side figure shows Panic receiving throughput under different traffic patterns. In phase 1, Panic divides the 64 available bandwidth of AES service across group 1 and group 2 using WFQ. So the receiving rate for group 1 is 2 times of the receiving rate for group 2. In phase 2, although the sending rate for group 1 drops to 50 gigabits per second, it does not change the receiving rate, since AES is still the contended offload. So in phase 3, both group 1 and group 2 sending rate drop to 30 gigabits per second, and the AES is no longer the bottleneck, thus the receiving throughput for group 1 and 2 is now the same as the sending rate. With this example, it shows Panic can isolate traffic using different policy. For more results in different policy, please check our paper. Finally, we measure Panic resource usage in our middle-end FPGA. As the table has shown, most of the on-chip logic resource is used by the crossbar and pivot block, and most of the BRAM resource is used by the packet buffer. In total, Panic only costs 11% LUT and 9% BRAM, which means our Panic design only uses a small amount of the hardware resource and can fit with any middle-end FPGA without timing or utilization issue. Please check our paper for more discussion about the feasibility of implementing Panic in ASIC. So the conclusion is, Panic is a full-line rate programmable NIC design that overcomes current NIC's limitation in multi-tenant environment. Thank you for listening.